what we're looking at today is parent functions and transformations. Parent functions and transformations. Now, there are different types of what we call parent functions. And a parent function is the most basic version of that function. So y equals x is just the equation of a line. And we call it a linear function. So y equals 2x or y equals x plus 2 are all going to be in the family of linear functions. And y equals x, or f of x equals x, so this here is the same as y equals x, is going to be considered its parent. Now, the reason they use parent or call it a parent function is because all the other types of that can fall back to the parent itself. They look like it. They're similar to it. So linear functions are always going to have a straight line, no matter if it's not as increasing as fast or faster. If it's up higher or lower, it's still going to be a line. Absolute value functions, no matter how we change it, it will still always look like a V. It'll have a V shape to it. Even if it's wider or narrower, or if we move it up or down, it still looks like a V. Yep, or we can flip it. Quadratics are always going to have this U shape to it. And the most basic for quadratics is y equals, or f of x equals x squared. Absolute value, y equals the absolute value of x. These are the most basic versions of each one. And the last one here is a constant function. It doesn't go up or down, it's just a straight line. Now we have domain and range. Now if you notice here, the domain, the x values are going to be all real numbers for any of these here. We won't deal with a graph or equation that won't have a domain of all real numbers. The only way that we will have a domain that is not all real numbers is if the value or the variable is in the denominator, or we're starting dealing with radicals. So there's some different functions there that we aren't looking at yet that have some restrictions on the domain. And the range is just our y values. Types of transformations is what we're going to look at. So we're going to be looking at these parent functions and being able to identify which one it falls under, which one's parent it belongs to, and then identifying the transformation that has occurred. So this is the first one we're going to look at. So there's two parts to it. The first is we need to identify its parent. So what is the parent function? So what do we think? What is its parent? We can look back at the first page to see. So what is...
Madison Hill, please come to the office. Madison Hill, please come to the office.
So the main characteristic of an absolute value has what? It looks like a... What does this one look like? So its parent is the absolute value. It's an absolute value function. Now the parent absolute value function, let's make straight lines. One. Yep. This one's a little off. One. So the one I just created, and you can write it down if you want, you don't have to, is the parent function y equals the absolute value of x. That's how it looks. Oh, you're good. All right, guys. So this is the absolute value function. But how did it change from that to the one we have looked at first, the one in blue? So we don't have to say in specific terms, but what happened to the whole thing? It went where? A little louder. I didn't.
The angle got smaller.
Right, so the angle got smaller. It's increasing faster, yes? So it got narrower. It's increasing, because what we would say is that it's kind of increasing faster and was, let's say, was moved. Up. Because the whole graph was moved up. Because here, the bottom of the V is at 0, 0. Here, it's now at 0, 1. It moved it up, and it's increasing faster. Questions on this here so far? Because what is this graph here? It is a graph of a line, so it is linear. This is a linear function. Now the linear function, its parent, would look something like this here, close to this. Now there's a few different things that are going on here. One of them is that it's actually been flipped moved up and up and right. Now we'll get into more actual technical mathematical jargon with actually how we explain this. There's actually more to it. And it's all revolving around this equation. Because if, remember, the parent function f of x is equal to x. Here we now have this -2 and -3 out front. They are affecting how the graph looks. They are affecting how this function works. Why would we say quadratic? Yes. That should be unlocked. So it's a quadratic because we have the U shape. So this here would be the basic, our parent function, our parent quadratic function. Well, we know it was moved right, because obviously the whole thing was moved to the right, yes? Opens slower, or opens wider, or is increasing at a slower pace, or increasing at 1/4. It has a vertical shrink by a factor of 1/4. That's actually more the technical jargon, because we'll talk about it as shrinking or stretching. So we kind of gotten the hang of this so far, not too bad. A transformation changes the size, shape, position, or orientation of a graph. A translation is a transformation that shifts a graph horizontally and or vertically, but does not change its size, shape, or orientation. So the first thing we're going to look at is a translation. That means we're moving it up, down, left, or right. We're moving it in one of the 4 cardinal directions. And the main way that this happens and this occurs is we're either adding or subtracting something from it, either outside or inside. So on the very last page, is it blank of the note sheet? Yes. I need to add a blank page in, or I need to add this in here. Go to the very back, since it's blank, the very last page of the note sheet. It's on the very back. Because what I want to add in is this. Linear. And I'll explain this here in a minute. Quadratic. Were you all able to get all those written down? Now, it didn't specifically say this because I think what they wanted is a more just looking at the graphs and telling this, but H, in all of these here is a left or right movement. Now, when we see it in the function, it is always opposite of what we think it is. Because if h is 2, in here we would have x minus 2. Well, since 2 is positive, the value of h is positive, it is to the right. But as it looks like it is negative because x minus 2. So really the best way that I can tell y'all to keep it straight with left and right is it's the opposite of what you think. If it's inside parentheses, inside absolute values with addition, subtraction, or adding or subtracting something from x, it's always opposite of what we think. Well, if h inside's up and or left and right, what do we think k is? Huh? Up and down. And it is exactly what we think it is. Because if it's plus 3, it's moving it up 3. If it's minus 3, it's moving it down 3. And we'll come back to this here in a minute. We're just going to deal with these two here. There are two others that we'll deal with. There's a third I don't even cover in here. So when we look at this here, the graph, I'm not going to ask you to graph any of these. But I do want us to identify the parent. So what is the parent? So the parent for x minus 4 is? It's a linear function because its parent is f of x equals x. F of x equals x. Now, its transformation, so g of x, I'll write it here next to it so we can see, is x minus 4. So we're subtracting 4 from the x, yes? Is it inside parentheses? No. So when we look at the functions I just gave you, that negative 4 minus 4 is taking the place of h or k? K, yes? K does what? Up and down. So it's moving 4 either up or, which one do we think it is? Because it is negative. So what happened to the graph? It went down 4. That's what it is. And if we graphed it, we would see that at every point on that line moved down 4. So if I were to graph it, the original parent function should be something this here, and the other one will be this here. It moved every point down 4. Are y'all starting to see this here? This is what transformations helps. It's not so much that we can graph it, because we could do a computer do that. But okay, I know that the function is moving down 4. So I know the original picture is here. Okay, everything is moving down 4. I get an idea of what the graph is doing. That's where this is helpful. Not so much actually graphing it, but having an idea and understanding of how this affects the function. What is it doing? Okay, our original graph, our original function. What's the parent going to be? Because it has what? Absolute value bars, doesn't it? So it's an absolute value function. So we know the graph is going to have what kind of shape? A V. The original function, f of x, equals the absolute value of x. So what changed between here and here? Yeah, we had plus 1, right? And it's inside, isn't it? Because if we add or subtract something on the outside, it moves up or down. If we add or subtract something on the inside, it moves it left or right. This here would be going to the, I heard one that got it, left. It is the opposite of what we think. Now, let's actually, because the parent function is going to be this right here. And we have this. Now, I'm just going to plug a number in. So for the value of x at 1. So when x is 1, well, 1 plus 1 is? So at 1, it's now at 2. Let's get a different color to help you guys out. So we have it at 2. Let's try 0. Well, 0 plus 1 is? Well, it looks like it's going down. Let's say negative 1 plus 1. 0. Negative 2 plus 1 is negative 1. But the absolute value of negative 1 is? So it moved it 1 to the left. Well, let's look back at the standard equation I gave you for absolute values. It's a times the absolute value of what? X minus h. But what do we have in here? It is plus 1. How can I make a negative sign become positive? There's only one way, is if I have a what? Because a negative, if I subtract a negative and a negative right next to each other make a. So really what I have here is not x plus 1, it's actually x minus negative 1. Negative 1, okay, now we can see it is to the left. And that's how it works for anything inside the absolute value bars, inside the parentheses. So that's why I say it's going the opposite of what we think. Since it's positive, it's moving to the left. If it's negative, it's moving to the right. Because that value of the movement, since it's minus on the inside, messes it up a little bit. So we kind of good with up, down, left, right. Yeah. And it's just keeping that negative thing in our head. A reflection is a transformation that flips a graph over a line called the line of reflection. A reflected point is the same distance from the line of reflection as the original point, but on the opposite side of the line. So like when you look in a mirror, the fact that on the mirror it flips your face, so the distance from that line of reflection, which is down the center of our body, is the same. It shapes the same. So, well, they called it P. Negative x squared. Now, what is the parent function? It is a quadratic. Why do we know that? It has the square. It has the x squared. Now, really, if the highest exponent, the biggest exponent, is a 2, it is called a quadratic. It's called a quadratic. So even if it's x squared plus 4x plus 4, we still have other variables. Since 2 is the biggest, it is a quadratic. Now, if you notice, there is a negative sign in front of the x squared, yes? So with our general equation, what would that attach to? It would attach to the a. So we'll flip back to the back, because I want to talk about the a. I'm going to erase some of this here, because so I can have a little more space to write. But a has two things. Is across the x-axis. So our x-axis, whenever we have negative a, it's taking it from above the graph to below. Also, this will be coming up in a minute. It is also going to be our vertical stretch or shrink. So go on and write vertical stretch and shrink down so that you have it. We'll explain it. I'll explain it more in a minute. Okay. Too far. So here, since a is negative, the sign in front of the variable is negative, not inside the parentheses, outside. This would be a what? Across x-axis. It'd be a reflection across the x-axis. And that's it. That's all. The only thing they changed was the negative out front. Any questions on this here? So what's the parent function? Linear. Linear is just x by itself, no powers. So parent function is this. So what happened to it? Reflection across the x-axis. Linear is an odd one because, well, actually no. In some cases, it could be the same as a reflection across the y, but it's only in a special case. Any questions over this here? Are we good with this here? Or so what would this be here? Parent function is x, which is linear, yes? And what did it do? So we had up 3. Up 3. It went up 3. We added 3 to the outside, so it's moving it up 3. Any questions on this here? It is a quadratic, yes. So its parent function be f of x equals x squared r. Quadratic. And how did it move? It moved right 2 units. Since it's minus 2 on the inside, opposite of what we think, negative, so it's moving to the right. Questions on this here? How about this one's parent function? Absolute value, it has the absolute value bars. Well, we didn't add or subtract anything on the inside or outside. Or across. Reflected across the x-axis. Okay. Vertical stretch and shrink. So I talked about this a minute ago. And this is really dealing with the number out front, our value of a. Now it's considered a vertical stretch if the value of a is greater than 1. If the value of a is greater than 1, it's a vertical stretch. It's increasing it faster. If the value of a is greater than 0 and less than 1, it is a vertical shrink. If the value of a is greater than 1, it's a stretch. If it's between 0 and 1, it is a shrink. Then if it is negative, do y'all know what it is? If it's negative 2, it's a reflection. Because the negative doesn't deal with stretch or shrink, the negative is a reflection. Because the reflection deals with its negative. So in most textbooks, when they talk about this here, a is greater than 1 between 0 and 1, they normally say the absolute value of a. It gets rid of that negative. So we're not really talking about the negative, we're just talking about a. Is it greater than 1 or between 0 and 1? So what's the parent function? Absolute value. So it's the absolute value of x. I'll say ABS, absolute value. What happened? Vertical stretch of 2. So that means that every point is going to increase by a scale of 2. So this here is the parent. 2, 4, 6, 2, 4. There's the new one. It's increasing faster by a scale of 2. If we do have time today, I will pull up a graphing program and start putting these in so we can see them a little better. I would agree. It's a quadratic because the exponent, we do have an exponent of 2. It is a quadratic function. Yes. By 1/2. So if the value of a is between 0 and 1, it is a vertical shrink. Any questions on this here? It is a quadratic. By a factor of 3. Any questions on any of this here so far? We go with stretch, shrink, vertical stretch, shrink, reflection across the x, moves up, down, left, right. Yes? Okay. I think we're good with these here, yes? So just for checking, this here would be what? Quadratic and a? 3/2 is greater than 1, so it's a vertical stretch by a factor of 3/2 or 1 1/2. I wanted to make sure because, again, we sometimes get in our head because it is a decimal or a fraction, it automatically is a shrink, but it is not. Now, just because up to this point, this one here, this problem, we've only had one. We've either it's stretched or it's been a shrink, it's been up, down, left, or right. We've only had one movement. We can actually have more than that. So this here actually has 3 different things going on with it. This probably isn't in there. Okay, that's fine. If y'all just watch this here. So we know that this is an absolute value function. It has absolute value bars, yes? So the first thing we notice, or I notice, is the negative out front, yes? So that tells me it's a what? Across axis. Okay, what else is there? Left 5, yes. So this had 3 different transformations. And that's it. Questions on this here? So this one here is a quadratic. What else do we have? Vertical shrink by 1/4 or 0.25, and is the 4 inside parentheses. So it is up or left and right's really only dealt with if it's inside the parentheses, is when we move left and right. And what this is really dealing with is a changing of the output or changing of the input. Inside this H, anything inside the parentheses is really changing the input, what we're dealing with an input value. Because squaring it, well, once it's squared, we're starting talking about output value, what's going to come out of the function. Before that, we're talking about kind of what's dealing with going in. So that's where we get the left and right. K, since it's outside, really it's affecting how the overall function looks or moves up and down, the output of it. Inside, input. Now, you probably haven't thought about this, but the fact that I've been focusing on vertical stretch, vertical shrink, emphasizing the vertical, is because there is such thing as a horizontal stretch and shrink. We don't delve into it too much because it actually, I'll show that in a minute, deals with, so let's just say quadratic. Affects the left and right movement. It affects the left and right movement. Because whatever this value is, if I want to know what the true left and right movement is, I have to factor the 4 out of it to really see that it's a left and right movement. It's a right of 2 with a horizontal stretch by a factor of 1/4. And it's not even dealing with the fact that this stretch is, we have to put it 1 over. So if it's a fraction, if it was 1/4, it's a horizontal shrink by a factor of not 1/4, but a factor of 4. So it is something I don't delve too much in here because of the fact that is just tricky. Does that make sense? And when we start dealing with it, I believe tomorrow, where we start actually manipulating these, or we'll be given an original function and we apply the transformations to them, we'll see how it goes. Because the order in which we do these matters. Because it'll change how the numbers look. But that is actually all we have for